The calculation part? Preferably after tomorrow. Because like tomorrow.
All right. Good morning. Today we are gonna continue on the example that I started on Wednesday class. We borrowed $5,000 at the interest rate of 8%, and we are gonna pay off the loan over the 5 years with 4 different plans. Then based on this example, I'm gonna talk about the equivalence concept in bridging economics. And then we are gonna talk about the equation. We are gonna derive the equation for compound interest rate. For simple interest, if you remember, the future value is gonna be P plus I and P. We are going to derive something like this for compound interest. How the future value can be defined as a function of P. When you invest P dollar in present time, after n years, if they are paying you I%, this is the money that you can collect if we apply simple interest. We would like to find an equation like this for compound interest. Good? All right. So the plan one, if you remember, to pay off the loan, constant principal plus interest. So every year we would like to pay the constant principal plus the interest. So we form the table like this. At the beginning of first year, which is going to be present time, we owe to the bank $5,000. We keep the money for 1 year. We should pay the rent for the money, which is going to be the interest, 8% times 5,400. So at the end of first year, we are going to owe the bank $5,400. So if you want to pay off the loan at the end of first year, you have to pay $5,400. So out of this, we are going to pay 1,000 constant principal payments. So 5,000 divided by 5, we are going to pay 1,000 plus the interest. So we pay to the bank this amount. We subtract this from the total unpaid balance. At the beginning of the first year, we are going to owe the bank this 4,000. We keep it for 1 year. The interest is this one. We pay principal plus interest. We are going to pay $1,320, and the total balance at the beginning of the third year is going to be 3,000. So if I want to draw this, it's going to be 1,400, 1,320, 1,240, 1,160, and last year at the end of fifth year, 10,800, 1080, sorry. So this was the first plan. So what we did in plan one, we pay off the loan over the 5 years at the same interest. Second plan, we only at the end of each year, we are going to pay only the annual interest. So, and principal payments, it's going to be paid off at the end of 5th year. So, plan to pay the interest at each year. Zero, 1, 2, 3, 4, 5. At the beginning of the first year, we owe $5,000. After first year, we have to pay $400. We don't pay anything for the principal. We are going to pay only interest. So $400 is going to be the money that we pay to the bank at the end of first year. We subtract this from the balance at the end of the year. We find $55,000. So we continue for all 5 years. And this year we have to pay the principal money as well. So the last year is going to be $5,400. So it's going to look like this. Plan 3. Plan 3, it's similar to the way or the structure that you pay off the mortgage or when you lease a car or get a loan to buy a car from the bank. So you borrow $5,000 from the bank and you want to pay off the loan over the 5 years, but you would like to have the constant amount of payment over the 5 years. So you don't want to have different values. So when you buy a house and get, for example, $250K mortgage from the bank, you would like to have a constant amount of payment for 30 years. So we can say constant payments. In chapter 4, we learn how to calculate this value. This is one of the things that we will learn in this course. But for now, we just want to represent this structure of the payment because we are looking for something else. If we find that, it's going to be 1, 2, 3, 4, 5. Same amount of payment over 5 years. The value is 1252. This is typically how the loan's working. You are gonna have the constant amount of payment over the periods of the loan. Again, we will learn in chapter 4 how to find this value. And plan 4, you want to pay, you want to wait until year 5, and you don't want to pay anything in the first 4 years. So you are gonna pay off everything on year 5. All payments at the end of 5th. Zero, 1, 2, 3, 4, 5. So you owe the bank $5,000 at the present time. You keep it for 1 year. You have to pay rent or interest for that $400. So you owe to the bank $5,400 at the end of first year. You don't pay anything, so this is coming to the end, beginning of the second year. At the end of second year, you owe the bank this amount plus the rent of the money or the interest. So you add these two, you get the total balance at the end of second year is coming to the beginning of the third year. This times 8% is gonna tell me how much would be the interest for the third year. I add them up. I will end up to this amount. If you want to pay off the loan at the end of third year, this is the amount that you owe to the bank. If you don't pay off, you have to pay, you are gonna go in the fourth year to keep it for one more year. The interest rate on this one is gonna be 503.88. You add them up, you end up with this. As you see, you don't pay anything in the first 4 years. And at the beginning of the fifth year, you owe this one. You calculate interest rate on that. So you have to pay this amount at the end of fifth year, and you are gonna pay off the loan. 7,346. Good. So, any questions so far? So these 4 different payments, you can see the structure of the payments are different. Different amount of the payment at the different timing. For this one, you didn't pay anything. For all of them, the values of the payment each year is going to be different. So these are the difference that you can see in the structure of the payment. But the similarity of these 4 payments would be all of them trying to pay off the loan that we borrowed over the 5 years at the same interest rate. So we borrowed $5,000 at this interest rate, and we want to pay off over the 5 years. All these 4 different structure of the payment trying to do this. So this is the similarity of these 4 payments. Good? So this is the point that now I can talk about economic equivalence. It's very important concept. Let's talk about it. So if you have 2 numbers, 3 and 3, these 2 are equal, so you can compare these 2. They are equal to each other. So economic equivalence is going to help us to define equivalence between 2 or more cash flow diagrams, CFD. So when you have cash flow diagrams, if the cash flow diagrams have the same economic effect, if your cash flow diagram, they have the same economic effect, we are saying that they are equivalent and they can be traded for one another. So there is no preference between them. So if you look at these 4 different cash flow diagrams, the timing of the payments are different. The amount of the payments are different. Here you see no payments until year 5. The others, they have something for the first 5 years. And the amount of the payment will be different. They look different, but they are equivalent because they have same economic effect. All trying to pay off the loan at the same amount, $5,000, at interest rate of 8%. This is what all these cash flow diagrams trying to do. So for that reason, this one is equivalent to this one, equivalent to this one, it's equivalent to this one. So if you think that 8% is reasonable, then these four different plan of the payment would be the same or would be equivalent to pay off the loan. So at 8%, they are going to be the same. So again, economic equivalence is defined to compare the cash flow diagram. So how it's going to help us to compare the cash flow diagram? Here we knew that since I first defined the problem and after I defined the problem, I draw the cash flow diagram. You knew that this cash flow diagram is for paying off the loan of $5,000 over the 5 years at this interest rate. The same thing for this one. Same thing for the other plans. So what if you didn't know about the problem? I just gave you these four cash flow diagrams. How did you know that these four cash flow diagrams are equivalent if you didn't know anything about the problem? So in this course, in chapter 4, 5, and 6, we learned about the techniques of equivalence. What we are going to learn in techniques of equivalence by using the techniques of the equivalence, first we set a reference point. Reference point can be any year. It can be time present, year 1, 2, 3, 4, 5, or future. But we are going to set a reference point. For example, I set the present time the reference point. So I will look at this cash flow diagram. I convert this cash flow diagram to this one, which is equivalent to this one, and I will find the value which is representing this. So these two are equivalent. By the techniques of the equivalence, I will find P1 and I draw the cash flow diagram here. I do the same things for this one. At the same year that I set as a reference year, by the techniques of the equivalence, I will find the p-value or the value at the present time for cash flow diagram 2. Do the same thing for cash flow diagram 3. And by applying the techniques of equivalence, I will find P4. Now, I compare these four. I can compare these four because in this four cash flow diagram, I only have one amount of the payment which occurring at the same time. So since they occur at the same time, I can compare them. There is no other payments on the this cash flow diagram. If P1 equals to P2 equals to P3 equals to P4, meaning that these four cash flow diagrams are equivalent, meaning that this one equals to this one, all four cash flow diagrams equivalent. If P1 is greater than P2, then I can compare the cash flow diagrams by comparing P1 and P2. So if P1, for example, is greater than this one, meaning that you are going to pay more in this cash flow diagram than this one. It's a paying because it's the arrow pointing down. So if P1 is greater than this, meaning that in this cash flow diagram you are going to pay more than cash flow diagram number 2. So you prefer cash flow diagram 2. So this is how the techniques of the equivalence can be applied to compare the different CFD and find the value. Good. So think about this, and I will call some of you. So what would be what would be the p-value for the loan problem that I defined here? What would be the equivalent value of these four alternatives at present time? So I set the present time as a reference here. What would be the present value? What would be the equivalent value for the alternatives? Number 41.
Would P1 be 6,200?
P1 is 6,200. 6,200.
Yeah.
Okay. P2.
I think that's 7,000. I think that one's 6261.4.
And last one.
And the last one will be 7,346.64.
Okay. Thank you. So number 55. What do you think?
What is the question?
The question is, what is the present value, what is the equivalent value of cash flow diagram for the different plans that we derived on the example? If I want to convert this cash flow diagram to something which is equivalent to that one with a value at the present time, what should be this value?
It would just be the p-values, right?
Yes. We are looking for that value. What would be that p-value? Jeremy said it should be 6,200, 7,000, 6261, and 7346. So let me call someone else. Number 14. Great. Yes. What do you think? See, in all four payments for different structure, what we are doing is we are paying off $5,000 that we borrowed at the present time. Means if I want to find the equivalence of this at the present time, this one is 5,000. This one is 5,000. This one is 5,000. This one is 5,000. Because they are doing the same things. They are paying off. What would be the economic effect of each of this cash flow diagram? All of them paying off $5,000 that we borrowed today. This is gonna do the same thing that this cash flow diagram is gonna do for us, or this one, or the last one. So we will learn how to find this 5,000 value in chapter 4, 5, and 6. But since we know what would be the cash flow diagram for this problem, it's gonna be, we can say that without any calculation, p-value for this one is 5,000. It's gonna be 5,000, 5,000, 5,000. So what I'm saying that there is no difference between having $5,000 today or having this value over the next 5 years. $5,000 today, it's gonna have the same value that this cash flow diagram is gonna have. Yes.
So does that mean that the P1 value that you calculated before, that's wrong?
This one you mean?
Yeah.
This one, Jeremy said, I just wrote this one here. This is the correct one.
Okay.
So what we calculate, if you remember, for plan 1, I said the total payment is 1,400, 1,320, this one, and this one. So these are the structure of the payment. So you cannot add them up because they don't occur at the same time. So Jeremy just added them up and said 6,200. So it's not right approach because this one has a different value of this one. You cannot add them up. This one is apple, this one is orange, so you cannot add them up. So you should, because the money has time value. If the money didn't have time value, you could add them up. Say, okay, this one has 6,200 value, this one has 7,000 value, this one has 6261, and the last one has 7346. But we know that the money has time value. So for that reason, you cannot add them up. You can just have the values, and then if you want to compare them, you should apply the techniques of the equivalence. Set a reference point. It can be any year, 0, year 1, 5, or late or future, and then trying to find the present the value which is equivalent to corresponding cash flow diagrams at the reference point. Then you can compare them. Is that clear? In chapter 4, 5, 6, we learned how to find this value. I didn't do any calculation, but since I knew that what is this problem about, I knew that the equivalent value of this cash flow diagram at the present time is $5,000. But if I didn't know anything about the problem, I should learn the techniques in chapter 4, 5, and 6 to convert the cash flow diagram to one single payment and then compare them. This is how we are going to use the concept of equivalence. We can convert the different types of the cash flow at the different type of the time we converted this cash flow diagram is occurring at the different points of the time. So in equivalence at the common reference point, I converted this to cash flow diagram at the common reference point. Here it was present time. You can choose different time, year one. Then if you convert this cash flow diagram to the common reference point, then you can compare them because they occur at the same time, and pick the best one. It's obvious that equivalence is dependent on the value of the interest rate. If I change the interest rate from 8% to different value, then this is not going to be 5,000. With this amount of number, if I change it to 7%, this is going to be different. All of them are different. All right. Any question about this? So now I'm gonna talk about compound interest formula, or the equation that we can use to apply the compound interest. We already talked about simple interest formula. So we would like to find a compound interest formula. So suppose you invest $P. You invest $P in a project which is paying you I% interest rate. So since you want to invest, the first arrow pointing down, you are paying out of your pocket $P. After 1 year, you want to know how much money you can get after 1 year. Since it's occurring at the future, I labeled this with F. P present, F future. So F, the project is gonna pay you your principal plus interest rate and that IP. So it's going to be P times 1 plus I. If I take P out of the parentheses, it's going to be P times 1 plus I. So if I tell you I would like to keep it for 2 years, not 1 year. So we would like to find the F. For 1 year, it's going to be P times 1 plus I, the value that I got here. So if you keep it this for 1 more year, it's gonna pay you this principal, which was this one. The principal was this one. You kept the money for 1 year, it's gonna pay you I% of this plus I times P through principal, the interest. Make sense? Now, here I have P times 1 plus I. Here I have P times 1 plus I. P times 1 plus I. P times 1 plus I is going to be 1. Here I have I. So it's going to be P times 1 plus I times 1 plus I. It's going to be P times 1 plus I over square. So F1, if you keep it for 1 year, it's going to be P times 1 plus I. If you keep it for 2 years, it's going to be P times 1 plus I power 2. 1 year power 1. 2 year power 2. I can show that if I want to keep it for 3 years, it's going to be P times 1 plus I power 3. So if the number of years is n, F would be P 1 plus I power n. if you invest in a project which is paying you I% compounded as a compound interest, then after n years, the money that you will get is gonna be this amount, P times, where I is the interest rate per compounding period, and number of periods. So I is the interest rate per compounding term, whatever is the compounding term. If it's yearly, monthly, weekly, I should represent the interest rate per compounding term. N representing the number of periods, and P is the present value or the money that you deposit, and F is going to be the money that you will get at the end of period. We call this formula as a single payment compound amount formula. Any question on this? It can be applied for the loan. Here I said we invested in a project. If you borrow money, meaning you get the money from the bank, you want to pay off after n years. How much you should pay off after n years? This is gonna be the same thing. You can see it has a single payment because it's dealing with single payments. Later on chapter 5, we will see that we are gonna deal with uniform series of the payment. They are not single, they have uniform series of the payment. The question is gonna say uniform series of the payment. So single payment representing this. And compound, meaning that we have interest rate as a compounding interest. So we can represent this, this is a mathematical form of this equation. We can represent this equation in different form. F equals to P, this term, this factor, we call this 1 plus I power n, called compound amount factor. This factor. This factor can be represented by this. F over P I N. If you see something like this, you should read in this way. We are looking for F. We are looking for F, future value. For a given P, whatever is here, it's given. Find F for a given P at interest rate of I over period of n. So we are going to use this term a lot in this course. So this is how mathematically we represent the equation. This is another form that we represent this one. So if I give you this, you know that you are looking for F for a given P at the interest of I over a period of n. Find F for a given P at the interest rate of I over period of n. I'm just repeating myself. Finding F when given P, we are looking for future value when the present value is given. So f equals to 1 plus I power n. We call this single payment compound amount factor. It's functionally expressed as f over p I% n. If you look at back of the book, Appendix C, you will find a table like this with some percentage on the top of each page. For the different amount of percentage, I think it's starting from 125%. So you have one page for each percentage on the top of that page. So the first column representing the n, which is this. If you want to calculate this factor, 1 plus I power n, first you find the corresponding n. Suppose n is 5. Then the first column is going to give you compound amount factor, or find f for a given p, f over p, which is this one. So for n equals to 5, read this one, 1.338. So for n equals to 5 and I equals to 6%, f would be p times whatever is the p, 1.338. So you could either plug in 6% here, 1 plus 6%, and then power to the 5, or you use this table and get this value. You will get the same number. It's going to help you to have less calculation. So if I look at this example, fine, you deposit $500 in the saving account, which is paying you 6% compounded annually for 3 years. So you would like to know how much you can withdraw after 3 years. So if I ask you to draw a cash flow diagram, you deposit it. So present time, 600. And after 3 years, you want to withdraw. So we are looking for F. So we deposit this amount, we are looking for F. It's obvious that we should use the compound interest formula. F would be P 600 times 1 plus I. The interest rate for this saving account per period of time is 6%. 6%. We kept the money for 3 years, so n is 3. So it's going to be 600 times 1.06 power 3. So either you use the formula and calculate this factor, you will end up to 595.50. So 500, sorry, it should be 500. 500 times this, it's going to be 595.50, or I can write future value would be P times F over P. I is 6%, N is 3. I'm looking for F. When P is given, F over P 6%, 3. This one. And read this factor from the table, Appendix C. Find the page for 6%, N is 3. The first column is 1.91. So 500 times 1.91. You will get the same. Any question on this? So the other columns that you will see here, the column later. Second set, this one is chapter 4, I believe, and this one is 5. Alright, let's look at this problem. This problem is looking at the other way of the calculator. We would like to have $800 at the end of 4 years. If the account is paying you 5% annually, how much should be invested to get $800 after 4 years? So cash flow diagram, the number of periods are 4. You would like to withdraw 800. So since you want to withdraw, it's going up. How much should be invested? We are looking for P when F is given. So if I'm looking for P, I should divide F by this one. So F equals to P times this. If I'm looking for P, I divide F by this one. So F divided P is going to be equals to F divided by 1 plus I power n, or F divided F times 1 plus I power negative n. So present value is 800 times interest rate is 5%, 0.05 power 4, and we will find the present value. 650.60. If you deposit this amount in this account, which paying you 5%, after 4 years you can withdraw $800. So here I define compound interest formula, single payment compound amount formula. I'm looking at this and define this one, single payment in this formula. We are looking for present value. We are not looking for compound amount. We are not looking for compound amount. We are looking for the present value. So a single payment present worth formula. The formula is going to look like this. P equals to F 1 plus I power negative n. What I derive here. Similar to this one, I had F equals to P times this factor. Here I'm going to have P equals to F multiplied by, here I had F over P. For a given P, we are looking for F. Now I should flip that, because for a given F, find P at interest rate of I over N period of N. The other form to solve this equation, this problem is we are looking for P for given F. F times P over F I N. F is 800. I'm reading this factor from table appendix C. So if you look at appendix C, second column, it says present force factor. So this factor is called present force factor. Present force factor for n equals to 4, I equals to 6%, 5%. It's right here, 0.8227. And you will get the same result. All right, we continue on method.